Welcome back to another explainer. Today we're diving right into the absolute foundational logic of discrete mathematics. We're going to break down the invisible language that powers literally everything, from the mobile apps on your phone to the most complex artificial intelligence algorithms.
And this isn't just abstract theory, by the way. This material forms the absolute bedrock of the information technology and engineering syllabus at institutions like CVM University and GCET. It's the foundation software engineers build their entire careers upon. If you want to speak the language of computers, well, this is the grammar.
Which brings us to the big question framing our exploration today. How do incredibly simple, binary true or false statements actually combine to build the massively complex brain of a modern computer? Throughout this explainer, we're going to follow a bottom-up approach. We'll start with the tiniest possible pieces of logic and snap them together piece by piece until we've built the architecture of digital reasoning.
Here is our quick 5-step agenda for today. We'll start with propositions, move into connectives, step over to logic circuits, tackle equivalencies, and finish up with quantifiers. Let's get right into it.
Section 1. Propositions, the foundational Lego bricks. So, what exactly is a proposition? Simply put, it's a declarative sentence that is definitively true or definitively false. That's it. It can't be kinda true, and it absolutely cannot be an opinion. In discrete math, a proposition is a statement of fact that gets assigned a rigid binary value, true or false, no exceptions.
To put that into perspective, look at the statement, Gandhinagar is the capital of Gujarat. That is a geographical fact. It is definitively true, which makes it a valid proposition. On the other hand, if I say, sit down, well, that's a command. It's neither true nor false. Or take x plus 2 equals 11. Because x is just a free variable, the truth is totally in limbo until we actually assign it a value, right? So, not a proposition.
Moving on to Section 2, Connectives, snapping logic bricks together.
You can think of these logical connectives a lot like the plus, minus, and multiplication operators in traditional math. We have conjunction, which acts as an and. We have disjunction, acting as an or. Negation, which flips a truth value with a not. We even have exclusive or, meaning one or the other, but definitely not both. And finally, implications. These are your classic if this, then that statements that essentially drive all computer programming.
Now, a truth table is how we visually map out every single possible combination for our propositions. Take a look at a conjunction here, an and statement. Notice how incredibly strict it is. If proposition P is it is raining and Q is I am home, the P and Q outcome is only true in that very first row where both are true. If even one statement is false, the whole conjunction just collapses.
Section 3. Logic circuits, moving from math to hardware.
We can literally translate that abstract math we just talked about right into physical logic gates within a circuit board. You see the mathematical concept on one side, and on the other, a physical piece of hardware called an AND gate. Electrical engineers literally take these exact truth tables and build microscopic gates out of silicon. Electricity flows through if the conditions are met and stops dead if they aren't. Your computer's processor is essentially millions of these gates constantly evaluating true and false at lightning speed.
We can also express all of this in binary code. By treating true as a 1 and false as a 0, we can run bitwise operations. When you compare the top number to the bottom number, bit by bit using an OR statement, which, remember, just needs a single 1 to be true, you result in a solid string of 1s. It's elegant and highly efficient.
All right, Section 4. Equivalences, visual proofs in logic.
De Morgan's laws are a perfect example of logical equivalence. They show us how to properly distribute a not across an OR statement. It's a bit like distributing a negative sign in algebra. If you want to say the exact opposite of P or Q, you don't just lazily slap a not in front. You have to negate both P and Q, and crucially, this is the trick, you flip that OR into an AND.
And you don't just have to take my word for it. By systematically plotting every possible true and false scenario for P and Q, we can calculate the results for the left side of De Morgan's law, and then the right. Notice how those final two outcomes are utterly identical. False, 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 true. When truth tables match up perfectly like this, the statements are logically equivalent. It's a foolproof visual proof.
Finally, Section 5. Quantifiers, abstracting the logic.
The universal quantifier acts as a blanket statement. It ensures a condition is true for absolutely every single value in a domain, represented by that upside-down A. Think of it this way. If we write a rule using a universal quantifier for a database of 1 million users, that rule must be strictly true for user 1, user 2, all the way down to user 1 million. If even a single user breaks the rule, the entire universal statement becomes false.
On the flip side, the existential quantifier just needs a single instance to be true, meaning there exists at least one valid example. We represent it with a backwards E. This is a much lower bar. If you're searching a massive database for a specific error code, the existential quantifier is true the very millisecond it finds just one occurrence of that error. It doesn't matter if there are millions of successful lines of code around it.
We can actually translate human language into computer logic just by mapping everyday examples to these quantifiers. All Americans eat cheeseburgers is a universal statement. To prove it false, a computer just has to find one single American who doesn't. Conversely, there is an honest politician is an existential statement. You absolutely don't need them all to be honest. Finding just one makes the entire statement true.
Now, watch what happens when we negate a statement. Negating a universal cheeseburger claim completely flips it into an existential claim. By stating it is false that all Americans ate cheeseburgers, you are logically declaring that there exists at least one American who doesn't. So, a negated universal quantifier seamlessly translates right into a positive existential quantifier. Pretty wild, right?
From the simplest true or false proposition to the logic gates directing electricity in your CPU, all the way up to massive quantifiers sorting through cloud databases, discrete math truly is the silent architecture of our digital world. So, the next time you run a search query, set a password, or just tap an app on your screen, take a second to ask yourself, how do these strict, tiny logical rules invisibly govern the software you rely on every single day?